Alright class, so we are done with gases, and what I'm going to do now, I'm going to summarize everything we talked about gases. So the first thing we talked about for gases, we talked about a barometer, right? We talked about a barometer. And if you remember, a barometer, what do we use a barometer for? We use a barometer to measure, to measure atmospheric pressure. So we use barometer to measure atmospheric pressure. And I said, if you ever watch the Weather Channel, you should do that. It's actually kind of fun. If you ever watch the Weather Channel, I don't know whatever does that nowadays. They talk about atmospheric pressure all the time. So a barometer is used to measure atmospheric pressure. And the equation that we use, if you remember, we said that the density of mercury times the height of the mercury equals the density of liquid times the height of the liquid. Okay. Then what we talked about? We talked about the ideal gas law, right? We talked about the ideal gas law, PV and RT. And what we said is like, when you're using PV and RT, what you really need to pay attention to are the units. You gotta pay attention to units, okay? You gotta pay attention to units. What we need ATM, liters, moles, and then Kelvin. And then what just we talked about, we said that when you read a problem, the problem is either going to be PV and RT, you have to plug it in and solve it, or the problem could be a changing problem, right? Or it could be a changing problem. And when you have changing problems, that's when you have at least 2 or 3 variables that are changing, right? So changing problem are when a couple of the variables are changing. Now we said the way you would do this, you would write down PV and RT. You would write down PV and RT, right? That's our ideal gas law. And you cross out the variables that are not changing, okay? Let's say, for example, I have a problem. It's a changing problem. I'm going to write down PV and RT. And I'm going to cross out the variables that are not changing. For example, I have the same number of moles, the R is just a constant, and it's the same temperature. So the only 2 things that are changing are pressure and volume. And then what I would do, I would say P1V1 equals P2V2. When you read a problem, figure out is it a changing problem or a couple of variables changing. If it is, write down PV and RT, cross out the variables that are changing, and then figure out the relationship. Or it's just a PV and RT, you're just going to plug it in. And don't forget about units. The other thing we talked about the average kinetic energy. And we said that average kinetic energy is proportional to temperature. So kinetic energy is temperature dependent and only temperature dependent. As long as you have the same temperature, you have the same average kinetic energy. Nice job so far. All right. Now, number 5. And we said because gases are moving around rapidly all the time, we have to talk about speed or velocity. We have to talk about speed or velocity because gases are moving around fast all the time around us. Okay, now when we talk about a velocity, which means speed, we talked about we do the root mean square, and that is 3RT over molecular weight. That is 3RT over molecular weight. That is going to get us the velocity of gases. 3RT over molecular weight. And don't forget a unit, okay? And we said this is a different R, is 8.134. It's a different R, and then you have to pay attention to the unit. Okay. Now, one thing that we said, okay, so 3RT over the molecular weight, the square root of that gives you the velocity of gases. But I also wanted you to understand conceptually, right? I want you to understand conceptually. And the conceptually is when the molecular weight goes up, what happens to the velocity? The velocity comes down. And that makes sense. The heavier atom, they cannot run around fast. The lighter atom, they can run around faster. How about temperature? When you increase the temperature, the velocity will also increase. So don't forget that. So higher temperature is going to be higher velocity, and higher molecular weight is going to be lower velocity. And what I really want you to remember that the lighter the atom are, the lighter atoms, they can run around fast. The lighter atoms are going to be faster. Yeah? Okay, beautiful. Now, what if we are comparing two gases? What if we want to compare two gases? If we want to compare the two gases, then the equation that we use is rate 1 over rate 2 equals the square root of molecular weight 2 over molecular weight 1. Basically, to compare, we want to look at a ratio. And this should be no surprise to you, because we said that the velocity of gases, it would be 3RT over molecular weight. Do you agree? So the velocity of gases is 3RT over molecular weight. Now, if you were comparing two gases and the gases are in the same room, what does that mean? If you're in the same room, that means you are going to have the same temperature, right? So the top part will go away. If you have you're in the same room, you have the same temperature, the R is a constant, is the same, that goes away. So the only thing that matters is the molecular weight. So the only thing that matters is the molecular weight. So when you compare the two gases, it will be the molecular weights divided by each other to get the ratio. Yeah? Okay. Beautiful. Now, almost there. Now, the last thing we talked about, we said that gases have a density, right? We said the gases have a density. And the density of gases, the equation, and the symbol is rho for density, is pressure times molecular weight over RT. And if you look at this equation, you can see that the higher the molecular weight, the heavier the atom is, the higher the density. Perfect. Now, I also said that if you look at the density equation, it has a molecular weight component, right? So it's also good to know that we could use molecular weight to figure things out also. Now, molecular weight is going to be equal to density times RT over pressure. Again, this is the same equation as this. I just rearrange it to solve for molecular weight. Same thing, I just rearrange it to solve for molecular weight. So far, so good? Okay. So this is good because this kind of summarizes everything we talked about gases. It summarizes everything we talked about gases. Now, are you ready to do some practice problem? Let's do this. Let's do some practice problem. Here is our first practice problem. Alright, do me a favor. Pause this video. Work this out, and then unpause me, and we're going to go over it together. Okay, now that you have unpaused me, I told you guys that I love these kind of problems. So let's go over it together. So you have two balloons. Both of them have helium in it. And they both have the same temperature and the same mass. Okay? Balloon A is being kept at a pressure that is twice that of balloon B. Which one has a higher volume? So if you look at this, you will see right away that, okay, this is gases problem. So if every time I have a gases problem, I'm going to write down PV equals nRT. So every time you see a gas problem, I'm going to write down PV equals nRT. So far, so good? Okay. Now, I have two balloons, but they both are filled with helium. They have the same temperature and the same mass. So they have the same temperature. So if they have the same temperature, what that means is I can cross out T, okay? I can cross out R, it's a constant. Now, they have the same mass. And we talked about before, same mass does not mean they have the same moles, right? But here, because they both are filled with helium, same mass will also mean same moles because they both are helium. So if they have the same mass, the mass will be divided by the same molecular weight of helium in both cases. So molecular weight of helium is 4 grams per mole. Now because both balloons are filled with helium, so they both have the same mass, divided by the same molecular weight, they would end up having the same moles. So they end up having the same moles in this problem. So far so good? Okay. So that means pressure and the volume are the parameter that matters. Pressure and volume are the parameter that matters. Now in this question, they ask you which one has a higher volume. I need you to pay attention over here. Now, if pressure and volume are the two we're looking at, because they're on the same side, if your volume goes up, what happens to the pressure? The pressure has to come down. If the volume goes up, the pressure has to come down because they're on the same side, because it has to equal to the other side. So far, so good. So, which one is going to have the higher volume? The one with a lower pressure. The one with a lower pressure. And it says balloon A is being kept at a pressure that is twice that of balloon B. So balloon B is going to have a lower pressure, and lower pressure means higher volume. Again, because they're on the same side. Sounds good? All right, beautiful. Which has the higher average kinetic energy? Hopefully you're yelling at me right now that's the easy one. Average kinetic energy. We said average kinetic energy depends on what? Depends on temperature. Do they have the same T here? Yeah, they have the same T. Because they have the same T, they're going to have the same average kinetic energy. Yeah? Okay, beautiful. Yeah, gases, a little bit conceptual question. You gotta get down for me. Are you ready for next problem? Let's do our next practice problem. Okay, pause me, do this, and then we're gonna do this together. So, you have water, liquid, and you're gonna apply electricity. If you do that, you can actually do this in real life. If you apply electricity to water, it's going to completely decompose into H2 and O2 gas. Don't try this at home. If you did, this is what you would get. Do not try this at home. So water would completely decompose to that. Now they ask you what is the pressure in ATM in the container. Now the first thing I want to say again, I want to say, okay, this is a gases problem. I want to write down PV and RT. It's not talking about velocity or density. I want to write down PV and RT. And is this a changing problem? This is not a changing problem. Why is it not a changing problem? No variable is changing. So it's not a changing problem. You good so far? You following me? Okay. So not a changing problem. So I'm going to write down straight up PV and RT. Now, what do they ask you for in this problem? What they ask you for pressure. Okay? So I'm going to isolate pressure. The pressure would be nRT over volume. Pressure would be nRT over volume. We're good so far? Okay. Now all I have to do is plug it in to figure out the pressure in this container. The first thing I need to figure out, so I need to figure out N, R is constant, and then plug in T and V to figure out pressure. I need to figure out N. And I know I've said this a couple times, and people make fun of me for saying that, but I'm going to say this one more time. Ideal gas law is for gases. You repeat after me. Ideal gas law is for gases. Ideal gas law is for gases. I know it sounds silly, but people make that mistake all the time. In this problem, I give you the moles of H2O. H2O is not my gas. H2O is liquid. So what is my gas? What am I looking for here? What I'm looking for here are the gases, which is the H2 gas and O2 gas. But what I'm giving you the moles of H2O liquid. I'm giving you the moles of H2O liquid. I'm asking you for gases. So I'm giving you one thing, but I ask for something else. Every time I'm giving you one thing, but I ask for something else, you have to use hashtag mole ratio. You have to use hashtag mole ratio to be able to figure out the item that you want. So every time I give you one thing, but I ask you for something else, hashtag mole ratio. That's really important. That's why it gets a hashtag. Alright, so let's do this together. So what I have here, I have 3.0 moles of H2O. I don't want H2 because that's not my gas. My gas is H2 and O2. So I'm going to convert it to the moles of the gas. So I don't want moles of H2O. That goes here. What I want on top, I want the moles of H2. Let's do H2 first. Okay, what is the mole ratio? Coefficients are the mole ratio. Coefficients are the mole ratio. So for 2 H2O, you end up getting 2 H2. Okay, coefficients are the mole ratio. So far so good. Okay, so that would cancel out. Just again, it's really key. We're going to cancel out the moles of H2 and we end up with moles of H2. Cancel the moles of H2O and we end up with moles of H2, which is what we want. Okay, so if I do that, what I end up getting is just 3 moles of H2 gas. Now, I'm going to do the same thing for the other gas, which is oxygen. So, moles of... Give me 1 second, let me have a little bit. Moles of H2O over moles of O2. Okay, now what's the mole ratio? Again, coefficients of the mole ratio, coefficients of the mole ratio. So again, water is 2 and O2 is just 1. Okay, so then the moles of H2O cancels out. I end up with moles of O2, which is what I want. If I do that, I get 1.5 moles of O2 gas. You following me so far? Okay, so now here's the thing about this problem. So when water breaks down, it forms 2 gases. So if I'm trying to figure out the pressure of the container, it includes both gases in there. Because I'm trying to figure out the pressure of the entire container, and the entire container has H2 gas and O2 gas that is formed. So for moles, what do? I would have to add up these two together. I would add up 3 plus 1.5, so I get 4.5 for number of moles of gases. So I'm going to come up here, I'm going to put 4.5 for N. You follow that? Again, because this question, they ask you what is the pressure in the container. And in this container, you have 2 gases. So I'm going to add up the moles of those 2 gases. Okay. Now, how about R is 0.08206. The temperature is 25. Okay. But don't forget units. I need to add 273. Okay. Divided by volume. Do I have the volume? Yes, the volume is given to me. Is 20.0 liter. Is already the correct unit, so I don't have to worry about that. Alright, not too bad. All I have to do is plug it in. Plug it in for me, tell me what you get. Yes, the answer is 5.5 liters because we are limited to only 2 sig fig, 5.5 liters. Yeah, how do you guys feel about this? Pretty good? Okay. Now, in this problem, if I had asked you for the partial pressure of H2, or if I had asked you for partial pressure of O2, then you would just use the moles of H2 or the moles of O2. But I didn't ask you for partial pressure. I asked you for the pressure for the entire container, so you had to add up the moles together. Okay, beautiful. So we're done with gases. We've done a lot of practice problem. Hopefully you get this down. Now let's end gases with a fun fact. You have heard of, especially nowadays, you have heard of greenhouse gases, right? Yeah, you've heard of greenhouse gases. Now, what do they talk about this? When they talk about the greenhouse gases, they always say that they contribute to global warming. So you hear about these gases all the time, greenhouse gases, you read about them, and they always say, yeah, they contribute to the global warming. Now, let's talk about these gases. So the greenhouse gases are carbon dioxide, about 76%, is methane, about 13%, dinitrogen oxide, about 6%, and chlorofluorocarbon, that's about 5%. So these are the greenhouse gases. Here's the thing. Yes, they do contribute to global warming. What people forget sometimes, and they forget to mention it, is that we need these greenhouse gases. We need these gases. Now, why do we need these gases? Here's why we need these gases. If we did not have these gases, if we did not have these greenhouse gases, the temperature on the earth would be minus 18 degrees Celsius. It would be really, really cold, and we can't live on this planet. So what do these greenhouse gases do? What they do, they absorb heat and they keep the heat. So the average surface temperature is usually at around 15 degrees Celsius. Okay, so they absorb heat, they keep it. So the average surface temperature of Earth is around 15 degrees Celsius. If we didn't have these gases, it would be minus 18 degrees Celsius. We could not live on this planet. So these are not bad gases. We need these gases. We need these greenhouse gases to keep the temperature of the surface of the earth to about 15 degrees Celsius. The problem is when we have too much of these gases. When we have too much of these gases, they're absorbing a lot of heat. They're keeping a lot of heat. So the average surface temperature is going to be higher than what is necessary. And that's our greenhouse gases. Sounds good? Okay, so you can show off your knowledge to people and talk about these gases. Beautiful, really, really nice job. I will talk to you guys next time.